Good evening, everyone. My name is Atul. Thank you, Dr. Gola, Dr. Diana, and Dr. Rashidi for taking some time out for me to defend this thesis in front of you. It's an absolute pleasure to defend this in front of you today. So, without further ado, I would like to start with the presentation outline, since it's that time of the day where it's 4 o'clock and I've kept it as short as possible, but trying to hit the key points as I go along. Just the presentation outline. I start with the introduction where I talk about the problem statement, which is just a statement of the problem, what it is and how I'm approaching it. And the applications, since it's part of mechanical engineering, it has to have industrial applications, otherwise it's of no use. So I have a slide in there, sneaking in with the applications in the industry. Now, the scope of the thesis, this is what I was set out to accomplish in this thesis. I'll talk briefly about what I was thinking of doing and what Dr. Gola told me, and it was really good. And the challenges, since I took this long to finish this thesis, I better have some good excuses for that. So I have a slide of challenges and roadblocks sneaked in there, just so that I could have some good excuses. Past research in this area. Well, there was a good amount of research in this area. Not a lot, but just enough so that I have good literature review for my thesis content to build something upon. And that was something I discussed in the past research section. Now, the model and problem approach using SolidWorks. What I did was just a synopsis of my thesis. I used a cascade flange. I took the geometry from the reference paper, built it in a SolidWorks software, and then did finite element analysis using SolidWorks simulation. So that's how I approached with the model is something I discussed in this. Finite element procedure. Thank God we have good software packages for finite element analysis today. But if we didn't have those, and if I had to do this analysis by hand, of course I would have needed to make a lot of simplifications and assumptions. But if I were to do it by hand, this is where I would discuss how I would do it. Thermal analysis, which is if you look at the topic of my thesis, which is probabilistic thermal and structural analysis of the flange. Thermal analysis is the first step, where I do the analysis thermally to see what temperature distribution looked like. That's what it is in this section. Structural analysis is the second part, which counts the combined thermal and structural loading effect on the thesis, on this model. Probabilistic analysis, this is something we would be testing, since in ideal conditions, doesn't matter what boundary conditions and what operating conditions there are, there are bound to be some externalities, or you could say scatter or irregularities in the model that could result in a really weird functioning of the model and failures too. So that's what we have taken care of in this probabilistic analysis section, and the results, discussing the results in short, conclusion, and future work, which is laying the foundation for further research in this area. So without further ado, let's get going on the introduction part. This is the problem statement as it reads plainly: perform thermal and structural analysis of the flange and use the results obtained to probabilistically evaluate the design problem. Well, it sounds simple, and it is simple, but it wasn't that simple. I'll bet on that it wasn't that simple as it sounds. So let's look at the industrial applications. This is just a teaser of the. I promise that you'll see more of this model further, but this is just a teaser to show what it looks like. It's used in high temperature and pressure fittings. It is supposed to provide high strength and high sealing capability. That's what the gasket is there at the bottom of it. And it should facilitate ease of pipe replacements periodically without lengthy delays. Now, this is the pipe. There's a mirrored model below this, and there's a pipe again. So when there are long pipeline transport or oil exchange, especially in Russia, where it's extruded from the ground and it has to be transported. This is very important, and similar applications too. So if there is a fault in one section of the pipe, you cannot change the whole pipe for that. So this really helps. Just take out the bolts, change that section, and you get going without lengthy delays. Now, scope of the thesis, as I was talking about, it was to perform deterministic thermal and structural analysis of the flange, assembly and match the results with the available research data. This is something I do the first step of my thesis, and the work is already there for this. So I just match the results. I do everything from scratch. I match the results with that, and then I proceed. Now you would think, if the results are already there, what new did I do? Well, being a master's thesis, I have to contribute to this field, something new that hasn't done before. So that's you see in the second one. Use these results obtained for probabilistic analysis of the assembly to study the behavior of the scatter or uncertainties in the parameters, and then aim at proposing a foundation for further work on this cascaded planned assembly problem. So the challenges I was talking about, first was the FEA software package. When Dr. Gola gave this problem to me, I really liked it, and I was thinking I could take the cross section of the plans, apply as a two-dimensional, apply boundary conditions to it, and generalize that over the circumference of the problem. But it wasn't so. It had bolts and it had gaskets, and the stress distribution was really different over the symmetry. So Algor wasn't a good choice for that, because it didn't really consider all the combined loading that I needed for this problem. Ideal choice would have been ANSYS, but then 2 years back we didn't have exclusive licenses for the ANSYS. So I settled on Cosmos Works, and as you know, from 2009 Cosmos Works changed to SolidWorks simulation. It's similar, but there were some differences which needed some adaptation time for myself. And then error in dimension in the source document. If you're reading that correctly, and I'm reading that correctly, that's right. It's a published paper in Boilers and Pressure Vessels journal, and it had a blatant error in the dimension that I was using as a reference for building my geometry. And I was in dismay. I was thinking it probably might not be the error, and I'm reading it wrongly. But I checked with Dr. Gola and talked to him, and he agreed that it's an error. And then I emailed the author of the reference paper, Dr. Mohammed Abid, and I emailed him to check if there's a mistake, and he didn't reply me back. But so me and Dr. Gola came to a consensus that there was a dimension. We came to a right dimension and went ahead with the problem. So that took some time off. And my dwindling motivation, of course, it was really tough for me to keep at it and finish this problem in time. Distraction of MBA, dwindling motivation wasn't enough. Distraction of my MBA curriculum was there too, to distract me from finishing this work earlier than now. And then when I was done with everything, and then I had a blunder in inputting the results. I had a decimal point blunder, which gave me really weird results in probabilistic analysis, and I was really frustrated. But finally, I caught that error, and it was the first time. Now, past research in this area. Most significant contribution is by Waters. I would like to emphasize that was in 1937, and the world has really changed since then. It was for a comprehensive planche design and became the basis of well-known Taylor-Forge method. So it was a really significant contribution by Waters et al. And it really acted as a foundation or a basis for this kind of problem. Of course, since it was in 1937, there were a lot of things that we have today they didn't have the luxury of. So it involved modeling of simplified plate and shell theory with known boundary conditions, and it was in two-dimensional model. So there were a lot of assumptions made for the simplicity of it. And then Murray and Stewart came along, and they performed flange analysis for taper hub flange. My model is the taper hub flange. That's why I put this on in there, removing many of the assumptions. And this was made in 1961. And they had a lot of assumptions too, and this was a 2D model too. But at least this gave a basis, something of a foundation for people like me or like Mohammed Abid, who did a lot of research in this area, to work as a reference paper. Now, the available work on this problem specifically. Most of the work, as I talked about this gentleman, Mohammed Abid, he has done most of the work with different variations in the boundary and operating conditions of the model. So one of them is determination of safe operating conditions for gasketed flange joint under combined internal pressure and temperature. So, and this is the document I was talking about. I've used as reference for the first stage of my analysis to match the results with. So, as I said, Here's only done the deterministic part of the model, deterministic analysis of the model. So that's the ideal conditions that the model would be, but it hasn't been adjusted for the variations or discrepancies that can happen in practical situations.
What year is that work?
This one?
Yeah.
1998.
98.
98. It's May 1998 Journal of Boiler and Pressure Vessels.
Okay.
So going ahead, I just have a small video. I thought it will take me less time, but it really took. This gives a better visual of how the assembly is assembled, for the lack of word. So these are the bolts that come in, go in the flange. The gasket comes up, and then that's how the flange assembly is formed. There's a mirrored flange of similar, the same mirrored flange on the other side. And that's how the continuity of the model goes on. So it took me 4 hours to do this, and in engineering terms you'll call it inefficient work, but I just thought it would give a better visual. So going ahead, I'll just talk about the boundary conditions that are imposed on this model. This is the cross section of the model, of course, with the board cross section cut in the center. Internal pressure is 15.3 megapascal. Bolt up pressure, which is the source of most of the stresses that act on this model, and source of all the problems that come in this model. On each board it is 254 MPa. Temperature, axial pressure, which is a component of the internal fluid pressure, is 5.1 MPa. And temperature of the internal fluid is 100 degrees Celsius, which acts as a combined loading for this model. And ambient temperature, outside temperature, is 20 degrees Celsius. Internal, since I'm considering convectional heat transfer, I'm considering the internal heat transfer coefficient at 150 watt per meter square per Celsius, and external at 20. And the constraints on this model, as I talked about before, this is the mirrored image of the model. For symmetrical reasons, I took the other part off. And as it says, the gasket flange is attached to a pipe of the same material. That's the pipe right here. And this is the hub, and this is the gasket. And I'm bolted to the other mirrored flange with a gasket in between. The flanges are free to move in either axial or radial direction. That's what is imperative for the functioning of this model. And bolts are constrained in radial and tangential direction. That's how they keep hold of the gasket two flanges. And as I said, if I were to do it by hand, these are just a short summary of how I would do it. I haven't put the whole derivation on there. But I have it in my report if you want to refer to that. So let us consider a three-dimensional partial differential equation of this form. And this is, I've taken the pressure and temperature and the work done into consideration, and that equates to 0. So the general derivative boundary condition is specified by this form. And then we have to apply that to a functional for finite element analysis. So that's the functional with triple integration for volume and double integration for surface area, and taking all the equations on all the components of the aspects. Then you have to apply that on element E. The function is obtained as with triple integration for volume and double integration for surface area. And then we come up with a simplex three-dimensional element, which we have extremized the above functional with respect to the unknown nodal temperatures. And this is how the result is reflected. B as elemental metrics and C as column metrics. Now, after deriving, that's what we come as in the result. The elemental metrics look like this, with triple integration for volume, double integration for surface area, and column metrics in the simple form. So thank God I'm not doing that by hand. This is the actual procedure that I followed. I constructed the geometry of the flange, gasket, and bolts, and then in SolidWorks, as per the drawings provided by Mohammed Habib in his paper in 1998. And the actual model of the assembly was prepared in SolidWorks simulation, which is just another finite element analysis software, which thankfully our CSU has exclusive licenses to, so it was easily accessible. The material geometry and thermal properties were obtained from from his same source. Boundary conditions were imposed and the assembly was analyzed for combined stress, intensity, and temperature distribution using FEA. Similarly for combined warmnesses and temperature distribution. Now this is how the assembly model looks like you saw the teaser earlier. Then when we measured, I used triangular mesh with the smallest size possible so that I could get most accurate results possible. So this is the triangular mesh, so that gives better results than the rectangular mesh. Now again, just a refresher for the boundary conditions that were imposed with. First I did the temperature analysis, thermal analysis, so this is what we require for that. And this is how thermal temperature distribution looks like after the thermal analysis, where maximum is 8.5 to 57.5. And since I realized while doing this that it is 22.5 symmetry, so 1/16 symmetry. So if you cut it from here and here, all the other 15 parts will be symmetrical, and it gives me a better way of imposing the boundary conditions and the pressure. So I just did it with that too for a 22.5 degree symmetry, and it gives exactly the same result as 88.5 and 57.1. So just for the sake of comparison, as I said, this is the first stage of my analysis, which is comparing the available work with my work. In the paper by Habib, the boundary conditions imposed, the same boundary conditions imposed, it was 57.2 to 88.2, and mine is 57.1 to 88.5. So it is pretty close, and considering the fact that I've reconstructed the geometry from the scratch, from the dimensions given by him, and analyzed it in a completely different FEA software, there is room for tolerances and errors. So and I talked to Dr. Gola, and he said this is acceptable. So I went ahead with that. And then finally did an analysis for stress intensity. Now if you ask me why I did stress intensity, the reference paper had stress intensity in it. So the ideal case for this would be to do one versus stress, because those give a good yield factor for the model, and they apply better to the metals and ductile elements. So I did stress intensity just for the sake of matching it with the results that are available in the research paper. And I did one versus stress too later. But for now, the stress intensity, the highest, the maximum is at the hub between the taper hub and the flange at the hub, and that is 282.4. And for the sake of comparison, as I said, with the thermal, in the paper it was 286, and mine is 282.4. And I would say this is, as I talked to Dr. Gola too, and he agreed that it is, since it's a completely different software, there's some things that are different. So these values are close enough to be accepted. So I went ahead with that. And then one assessment, which is something which we usually do with these kind of problems, which gives a better picture of what kind of stresses will be induced in real time. It gives a maximum of 53.2, and unsurprisingly, that's at the hub too. So just an overview of FEA results that I came up with. Temperature distribution 57.1 to 88.5, maximum stress intensity of 282.4, maximum one versus stress of 253.2, and both at the hub. So now this is the main part of my thesis, which is probabilistic analysis. So when I came up, I had to come up with random variables that could be the source of discrepancies in the working of this model. So there were material properties, input pressures, input temperatures, boundary conditions, and physical dimensions, of course, that were changed for each run. And in total, there were 40. So when I talk about this sounds really short, but there were 40 random variables, so I had to get an upper limit and lower limit for each. So I had to run this finite element analysis for each run, and there were 82 runs in all. So there was a lot of work, and I had to keep a lot of documentation so that I could fetch those numbers for the results. And then the probabilistic analysis was carried out based on first order reliability method, which is FORM in short. If you ask me why didn't I use SORM, which is second order reliability method, this is a linear model, and SORM usually gives better results if it's a non-linear model, because FORM takes a lot of assumptions, but SORM doesn't. So FORM was good enough for this one, so I stuck with FORM. 40, as I said, 40 random variables were used to compute maximum stresses on various probability levels from 0.001, which is 1%, to 0.999, which is 99.9%, for both onennesses and stress intensity. So cumulative distribution functions, which is CDF, which is the curve that comes up, which is, if results are right, it gives you a very smooth S curve, which since I had made that error earlier, it was really haywire. But I finally got my act together and got that fixed. And then the sensitivity factors it pinpoints the factors or the random variables that are causing most of the influence on the model. And that are used in the Thesis software, which Dr. Gola provided. And this is, as I said, if the results are right, it gives a really smooth curve from 0.1% to 99.9%. So the for 1% probability, as you would guess, it's much lower. It's 154.86 for stress intensity, and for 99.9%, it's 494, 39.94. So an excerpt from Dr. Rashidi's bearing and lubrication class, where he talked about if this is the application for aerospace, they would need very low defect rates. So probably I'll have to do it for 99.999% too. But for this one, it's not a very critical operation. It usually doesn't involve lives. So 99.9% probability was good enough, and that's the highest stress input for that. Now these are the sensitivity factors, and as I said earlier when I was showing the model, volt-up pressure, which is the pressure applied on the board, is because of the functioning and working of the model, has the most influence of us, and followed by the flange height and shoulder height. This is because when flange height or shoulder height increases, it puts more material in the flange, and of course it really distributes the stresses, and less stresses are used. This is for 0.1% probability, and since it was a linear result, for the probabilities in between, you could look at that in the report for all the probabilities. But I just took the extreme values, 0.1% to 99.9%, and if you see, shoulder height really shoots up, which tells you that shoulder height, when it's increased, it really influences the stresses induced. And volt-up pressure is there, but it lowers. After a certain degree, volt-up pressure really doesn't play that important role in this model. Now the cumulative probability for oneness stress is a smooth curve again, and it's from 132.89 to 284.62. So the sensitivity factors for this is, of course, again, the volt-up pressure stands up amongst others. Flange height and shoulder height is there. And for 99.9% probability, it's volt-up pressure again, but it goes down a bit, and other influences are there, as you can see.
Where are the material properties? Modulus of elasticity.
If you count, these are 32, and
no, just show it over.
Yeah.
That is the modulus of elasticity.
This is for the flange, and modulus of elasticity.
And then how about alpha, the coefficient of expansion?
Coefficient of expansion, it's expansion.
Yeah. We're not able to read this.
Oh, I'm sorry. There are so many crammed in there. I tried to use entire space of the page, and still too small. Good that you told me to take out the 8 factors, 8 random variables that weren't having any influence on them. Otherwise, there would have been 40 here, and it would have been impossible to read as it is. So, just the results, and there's a summary of results. We observed that the overall model thickness, flange height, shoulder height, cascade diameter, and volt-up pressure have huge influences on the maximum stresses. It is followed closely by flange outside diameter, shoulder outside diameter, thermal conductivity, and point inspiration. Now, just to conclude, why are we doing this? What's the significance of doing the probabilistic analysis? It is our ultimate goal to model a really robust assembly, so that it has a very good reliability and it doesn't fail in most cases. We cannot say in all cases, because some discrepancies are still there. So just just reading it to you, all engineering systems function reasonably well under ideal conditions, but robust design, which our ultimate goal is, continues to function well when the conditions are not ideal. And in practical situations, that's what happens. With a boulder pressure, even though it says 254 megapascal, sometimes there could be an impact loading, and it could go to 270 or 280, who knows, and it could fail because of high impact loading. So robust design is one that has been created with a system of design tools, and this probabilistic analysis and sensitive vectors is one of those tools that gives the designer a good idea of what to take care of, what are the critical random variables that he needs to really pinpoint and do adjustments so that it doesn't fail. And robustness means achieving excellent performance under a wide range of operating conditions, and probabilistic design and robust design go hand in hand, as I said. Since it is one of the tools for the designer to make a robust design, they go hand in hand. Now in this thesis, as I said, I did the deterministic analysis, which was already done earlier, and then I added the non-deterministic factor to it, which is the non-deterministic approach, the probabilistic approach to it, to find the critical factors that are really influencing the stresses. They are supported by a deterministic analysis, supported by non-deterministic analysis. The novelty of this approach is the probabilistic evaluation, as I said, is the finite and solution for the design problem. So probabilistic analysis helps the designer to choose a suitable material and geometry from the available sets of parameters. Now the cumulative distribution function, as I said, gives you a good probability distribution and the stresses induced at each probability. So depending upon the criticalness of the function or the application, you choose from what kind of probability. For aerospace application, you choose the highest reliability factor. For transportation where lives are not involved, you'll probably choose something in the middle. So it's up to the designer to choose what kind of probability he's looking for. And the sensitivity factors, as I said before, is the relative importance of the variability or uncertainty of all the input factors and the influence on the resulting fatigue line. Now, these are all the parameters the designer will be looking for designing an optimal reliability-based design. Slight alteration to all these, of course, would have a significant impact. As you saw in those graphs, there was quite a difference in each probability for each random variable. So in this thesis, our goals were to first check the area of maximum stresses, which was half of this assembly, and then deformation, and then carry out probabilistic analysis to get a better picture of the effect of random variables on stresses. Now, this sets up well for the future work. Now, there are a lot of variations in this model that could be used. I used one of it, which was 100-degree fluid pressure and water pressures that I used. There could be different combinations of it that could be used for different applications. And the random variables that I used could be used as a basis for doing further studies in this topic. So I'm sure you'll have a lot of questions. I'll try my best to answer those.